As you said, my name is Ryan Mohr. I work for AIMDYNE Inc. I will be talking about combining programmable potentials and neural networks for materials problems. I'm pretty sure that no one knows what programmable potentials is. But before we get into it, sorry, jet passing overhead, if you could hear that. So collaborators on this project from the AIMDYNE side, myself and Dr. Alan Nabila, Professor Igor Mezic from Santa Barbara, and Dr. Maria Fanobarova. From the QChem side, we have collaborators of Dr. Xintian Feng and Professor Martin Gordon, who's in the chemistry department at Berkeley. They lent us their chemistry expertise. And we also collaborated with Professor Ruslan Salakhutdinov from CMU. And we had a sequence of graduate students from master's and PhD level working on this project at different times. This is Soham Ghosh, I believe, is at Google now, Ananta Attari, and Muchao Yang. And this work was supported under DARPA's AIE program on Artificial Intelligence Research Assistant. So, intro to the problems that we're going to care about. We'd really like to compute and infer macro level properties of chemical or material systems. So this connects with the previous talk by Marta. So force field methods in MD simulations can be used to infer these, but however, we can predict erroneous values due to not being accurate at the quantum level. So ideally, we'd like to simulate from first principles and scale as needed to get the properties, but obviously this is computationally infeasible. For real size systems, solutions time to scale exponentially with respect to the number of electrons. So density functional theory and periodicity assumptions, these QMMM methods mitigate this somewhat, but it's still infeasible for many systems. So our approach to this is to construct a generative model by taking classical MD potentials such as Lennard-Jones, which capture the long range interactions accurately, and then combine these with neural networks, which encode the quantum level logic and correct the near range interactions. So the rest of this talk is going to introduce the programmable potentials, its classical formulation, and then introduce the new formulation, which incorporates neural networks. And then we apply this to the problem of adsorption of hydrocarbons in a zeolite framework, which is quite common in industry applications, and then we'll go over results and some conclusions and open it up for questions there. So the program potentials, this was first appeared in a PhD dissertation by Dr. Gunjan Thakur in 2000 level. It was really at that time developed for encoding information in coarse-grained models for self-assembling systems, in particular soft biomolecules. We extended this in 2016 to the study of combustion chemistry on an R. Muri project. You can see the references there. So the main idea is captured in this figure here. So we either have experimental data or data from simulations. We take some pairwise potentials, and then we look at the system really hard and discover the coarse level interaction rules. This then goes down and we build logic functions that then get smoothed out into what we call encoding functions because they encode the coarse level behavior. Then these multiplicatively modify the pairwise potentials to get the modified potentials, and we get the n-byte potential, which is taken here in this formula here. So VJs would be the pairwise potentials between molecules J and K, and SJK would be the encoding function that modulates this. So mathematically, to build these encoding functions, we start off with a class of Boolean functions, which we take as an indicator functions on these on this half-open interval, 0 to R. So this is really just a proximity function with a cutoff distance R. We then combine these according to the coarse level logic with ands, ors, and not gates, and then replace the Boolean functions with smooth variants. So as an example of this, down here, we have the simple system where we have molecules A, C, and B. This is a cartoon. And we have proximities between A and B, A and C, and B and C. And the course level logic of this system would be that when B is far away from C and C is close to A, that bond is on, but when B comes close, the bond between B and C turns on, and the bond between C and A turns off. So this is quite simple, but the issue with this, that for anything past a simple system, the reaction logic becomes quite complicated and takes a lot of ingenuity and a lot of man hours to find it out for a moderately complicated system. So the idea with programmable potentials to neural networks is to actually use neural networks to replace that human-centric, high effort process of finding the course level logic and constructing the encoding functions. So another benefit of this is that implementation in something like PyTorch or TensorFlow allows us to auto differentiate the potential, so we can automatically get the force fields for MD simulations, so we don't have any type of error-prone human differentiation step as well. So like I said, we just kind of replace that whole human-centric workflow there with a neural network encoding function. We still retain these pairwise potentials, and this allows us a generative model that should extrapolate well outside of its training domain. So what do these encoding functions look like? So we take in the positions of all the molecules here. We get fed into the encoding function and compute required pairwise distances, because the encoding function will depend on different proximities of different atoms. These get fed into the computation of proximity function, which then gets fed into this fully connected neural network, which is supposed to learn the, say, quantum level logic, right? And these are what these kind of smoothed proximity functions look like, right? If n goes to infinity, we'll recover that Boolean logic on, say, 0 to alpha in this case. So we applied this problem to absorption of hydrocarbons in the zeolite framework. Zeolites are these doped nanoporous silica catalysts. These are silicon and oxygen not lattices, but frameworks. And when we dope this, we usually replace a small number of silicon atoms with aluminum atoms or something else. And these are widely used for catalytic frameworks for cracking and dehydrogenation on oligomerization. So in here, we have the silicon atoms, we have these red oxygen atoms, and then we have this hydrocarbon in here that gets absorbed into this pore here. So for our specific applications, we generated data sets for both the M-doped zeolite framework and the doped zeolite framework. And then we also generated data sets for methane, ethane, and propane for undoped, and then methane for the doped zeolite framework. And these were generated by really high fidelity QM-MM computations from QChem. I'd like to point out that the quantum mechanical region is really determined by a connectivity-based computation. So it looks at the closest silicon atom to the hydrocarbon and looks at the 4 connected oxygens and then the 4 connected silicon atoms that are closest to the hydrocarbon. So in this picture on the right, we have silicon in this off-white color, oxygen in this red color, and these magenta surfaces here, they're actually composed of a bunch of little spheres, and that's where we actually have energy calculations for the position of the hydrocarbon in this data set. What's interesting to note here that the undoped zeolite has 12 chemically distinguishable silicon atoms called symmetry regions, and we label these T1 through T12. So we have a data set for each symmetry region, and what we do later is that we're actually going to just train on the T1 symmetry and extrapolate to the other symmetries. So the models that we looked on, we have a baseline model that's just pure Leonard-Jones, and then models 2 through 6, they are actually the kind of classical programming potentials paradigm, where we chose a hand tuned encoding function. And then there's different optimizations that were applied to each of those functions. They had the same logic though. Of particular note, you can go back and read this if you want, but case 5, and case 7 are the most comparable. So case 5, it's Lagrangian's pairwise potentials. We use the QChem provide Lagrangian's parameters, and this one has the connectivity-based definition of the quantum mechanical region. And then 7 is the connectivity-based, is the same definition of the quantum region, but the encoding functions are given by neural networks. Cases 2 through 4, those actually use a radial-based distance of the quantum mechanical region, which actually intuitively you would assume defines the quantum mechanical region, but apparently the actual connectivity-based definition is more accurate in simulations. So as I said, all these models were trained on T1 symmetry and then tested on symmetries T2 through T12. And I would like to point out that these networks are typically pretty small. These are 48 layers, 8 nodes per layer, or in one of the transfer learning cases, 16, 32, 64, 32, 16 fully connected layers. And I also like to point out, we try to learn a global encoding function for each unique atom pair type interaction. So on the zeolite framework, we just have silicon and oxygen, and those interact with the carbons and hydrogens of the hydrocarbon. So we really only have 4 unique atom pair type encoding functions. So we have the oxygen hydrogen, we have oxygen carbon, and then we have silicon hydrogen and silicon carbon. And so every action that was region, they share that same global encoding function. Metric that we're going to show here is this mean relative error. So it's the energy EI here, that's the energy from the data set, sorry, the energy of the data set at sample I. This is the programmable potential model energy at sample I. And we scaled this just by the range of the data. And then we divide out by number of samples. So first set results for methane and ethane in the undoped zeolite. And this is the results on the T1 symmetry. Again, I'd like to just highlight case 5 and case 6 are the most comparable. The only difference was between the encoding functions, hand tuned here, neural networks here. Does better on for the neural network case. Same for the methane as well. Case 6 is a little bit, I know it does better, but it has an additional degree of freedom for optimization where it can actually optimize Lagrangian's parameters, whereas case 5 and and the neural network case did not. So moving on to the generalization. So this is results for the T2 to T12 symmetries. What we're actually showing here is we compute the mean relative error for T1 through T12, and then we average all of those errors to actually get these bar plots here. So again, the neural networks are beating out case 5 for methane, but it does slightly worse on the methane. I'm not entirely sure about that. The reason why that is, I think it's because one of the symmetries, I think T9 has extremely different behavior for the energy surface than the T1 case. And so they have quite large errors there. So that may be the reason why it's not doing so well here. So moving on, we're looking at here the generalization of the CH4 encoding functions to C2H6. So what we did is we took the T1 symmetry data for the methane in the zeolite framework, and we trained the encoding functions there. And then we fixed those, and we just built a model for methane, the C2H6 in the zeolite framework, and used those as basically initial conditions. So here in blue, this is the baseline. This is the pure Lennard-Jones potential. In orange here, this is the model for C2H6 using the CH4 encoding functions with no additional training using the methane data set. Green here, we use the CH4 functions as the initial conditions, and then we trained for additional, I believe, 50 epochs on using the methane data. And then red is the neural network trained directly on C2H6. As you can see here, orange beats the baseline, does not beat the network trained on C2H6 directly, but with a little bit of retraining of the CH4 functions, we can get pretty close, at least on the training set, to the pure C2H6 encoding functions. But if we look at the rest of the symmetries too, often using the C4 functions with a little bit of additional training, we actually do beat the pure C2H6 encoding functions, which shows that these generalize pretty well to different data sets. Moving on, this is the same as generalization of CH4 to propane, C3H8. Again, just using the initial C4 as initial condition, a little bit of retraining in green, and then the native C3H8 encoding functions. And again, it's very similar results. A little bit of retraining gets us very close to the C3H8 encoding functions directly. And then a harder problem is generalizing from the CH4 in the undoped zeolite and then transfer them to CH4 in the doped zeolite. Remember, the doped zeolite is the zeolite with some aluminum atoms replaced by aluminum atoms. We did actually have to train aluminum and hydrocarbon interaction encoding functions from scratch. We don't actually have the native one here in this picture, which I apologize for. But blue again, pure Lagrangian baseline, neural network without adaptation in orange, and then with a little bit of retraining, we can actually improve quite a bit on the just the CH4 initialized encoding functions. So I think I have 3 minutes left, so going to conclusions here. So we presented the programmable potentials methodology in context of absorption of hydrocarbons in zeolite frameworks. Here we really get generative models by using a structured form. So that was, again, the parametric Lagrangian potentials, which captures the long-range interactions correctly. And then we have encoding functions, which multiplicatively modify the Lagrangian potentials to correct for these near-range discrepancies. The generative form allows good generalization outside the training set, and it also allows generalization from simpler hydrocarbons to more complex ones. I do like to point out here that this is where we had to use the higher capacity neural networks. When we tried to generalize using just the, say, 8x8 fully connected layer with the 4x8, while it did generalize well to different symmetry regions, it didn't actually generalize well to the more complex hydrocarbons. So there seems to be some relationship between the capacity of the network and the ability to generalize to the more complex hydrocarbons, which we haven't untangled. And then we also generalize from the undoped encoding function to the doped. A little bit of retraining, we are actually able to improve the models. So I will stop there and ask for questions.